Our next speaker will be talking on CO2 as a performance-enhancing admixture in ready-mix concrete. And you can see our
second code.
Yeah, our second code there. So write it down because it's going to disappear in 3, 2, 1. Put up the other one. So our next speaker is Sean Monkman, and he's the Senior Vice President of Technology Development for CarbonCure Technologies. He oversees the company's research and intellectual property efforts as they develop scalable carbon utilization technologies to create more sustainable concrete. Sean holds a PhD in civil engineering from McGill University. His career has included more than 25 years working in concrete materials, including more than 15 years working on CO2 utilization approaches. Sean has extensively presented and published on beneficial carbon dioxide utilization in concrete production and is a co-inventor on over 120 issued and pending patents related to the work. In 2003, he was recognized with the ACI Foundation's Jean-Claude Romain Innovation in Concrete Award. Sean is active within ACI on our 212 chemical admixtures, 236, 241, 329, and was also chair of 130, the Sustainability, and 601C, Concrete Construction Sustainability Assessor. So please welcome our next speaker, Sean Monkman.
I'd have to double check what bio you have in front of you. I certainly did not win that award 20 years ago. It's at this conference. 2023. Oh, sorry. Thank you. Great. So it's great to see a full room of people. I'd like to thank the organizers for putting this session together. This is kind of one of those evergreen topics you could probably have at every single convention, talking about the role of admixtures to make concrete more sustainable. And I'm glad to see you've got a good group of speakers together. I'm going to be talking about some of the work we're doing at CarbonCure. And just to start off as a bit of a basis, I like to refer to what the industry is trying to do. This is the GCCA, the Global Cement and Concrete Association's roadmap for creating more sustainable concrete. They've divided the actions we can take to move to a more equitable and sustainable industry into a number of different pods. So obviously there's things we can do on the cement side, the fuels we use, the amount and types of SEMs we can use. But what you'll notice is the biggest blob there, the purple blob, 36% of the activity that is needed to reduce the carbon footprint of the industry is related to, as they call, carbon capture, utilization, and storage, or these other innovative activities that are just emerging and we don't know anything about them yet. If we look at what this means over time, there isn't a lot going on that purple slice right now, but that's ramping up. You can see, if you're talking about carbon capture, to meet those goals, there's supposed to be one cement plant capturing CO2 coming online every week every month from 2030 onwards to get to that goal. So with that ahead of us, it's just kind of a big motivation to look at other things we can do with CO2. We're not going to be burying it all underground, but can we derive value from it, particularly within the cement and concrete value chain? So this is what we've done with CO2. We've come up with a system to use CO2 as an admixture. So if you look on the left-hand side, we just have a representation of a tank of cryogenic CO2 communicating with a control box, which then injects the CO2 in a controlled dose, like an admixture, into the concrete, whether it's a truck mixed situation or a central batch situation. And that is integrated into the operations of the batching control system. It's just plugged into the main batching computer. So it's just another ingredient that you're putting into your concrete. And this is an example of a tank and a control system. So we can just retrofit this at a concrete plant and push it on and away we go. Very similar to admixtures, same idea with an admixture. You have a supply of an admixture at the concrete plant. That supply is in communication with the dispensing unit, which puts it into the concrete in the desired amount at the desired time. Same idea with CO2. What does CO2 look like when you're using it as an admixture? Well, if it's a cryogenic CO2, it's in a liquid form, but when you inject it, it's now at atmospheric temperature and pressure. It's no longer liquid. It flash converts to a mixture of solid and gas. And if you looked inside the mixer, it would look something like this. So you have this flakes of CO2 going in, adhering to the wet mixed concrete. And then we have a chemical reaction taking place. And what do we see if we just go back a little bit before the CO2 got there? Hydration had started. We have cement contacting water. So we get a little bit of dissolution, ions going into solution, the pH goes up. Then we add some CO2. This is extremely simplified chemistry. You do not form a CO3 2 minus ion to react with the calcium, but let's just say that's what happens. You end up with calcium carbonate. So you form this new mineral inside the cement paste as it's being mixed, and then that provides a little bit of a catalysis. So we see in response to the removal of calcium from solution, we have an undersaturation in the solution, and we end up forming some CSH gel alongside. It looks something like this. This is an SEM picture of a mineral, so we can find evidence of this in just a paste produced for purpose. We can find these minerals in response to the CO2 that's formed. In this case, we're seeing something that's about 400 nanometers across, and it looks vaguely cubic. And what happens when this is now in your cement paste is you can actually make the concrete stronger. So we did some work just to say, let's see what happened. We have this system. We set up a CO2 injection system at a truck. In this case, it was pre-industrial. We're injecting CO2 into the truck at the wash rack, so to speak, so after the concrete had been mixed. And we can see a bit of a dosage response to the concrete. In this case, we had 3 doses, 0.07% by weight of cement, 0.16 and 0.22% by weight of cement. We refined our dosages in the future after this, but kind of odd numbers. But what we found is that we got a bit of a bump in strength with the low dose, a bit more of a bump with this mama bear middle dose, and in the 3 bear situation, we have a kind of a loss of the performance if you go too high. So we see this kind of chemical response. There's an optimum in there that you need to kind of work with when you install the technology and find that. Those strength gains, they do manifest themselves not only at early ages when we're unlocking this benefit, 1, 3, 7 days, but we can see 28, 56, 91 days, that strength benefit being maintained. In this case, another one, pre-industrial, one of the first times we did this in 2014 in Toronto. So this mix had 20% slag, which is one of the themes I'll get into. But once we've industrialized the technology to a retrofit, now we have it integrated into the batching cycle. No more dosing CO2 at the wash rack. Let's make it very simple. So from this producer, they have a 4,500 PSI mix, 564 pounds of binder, and it's a ternary blend. We have fly ash and slag in this case. The dose to get this observed benefit was 0.2% CO2 by weight of the cement, not the cementitious. Not shown, but there was no impact to the air content of the mix. There was no impact to the slump. So for the people placing and finishing the concrete, they didn't notice any difference. But if you measured the mechanical performance of the concrete, they observed an 8% benefit at 7 days and 7% at 28 days. So if you did the math, what we've done is effectively use the CO2 to increase the efficiency of the cement that's in the mix. So we've gone from a 13.5 PSI per pound of cement up to 14.4 PSI per pound of cement. And as we've taken this technology to different concrete producers, of course, they have different cements. Each local producer will have their own nearest cement or cheapest cement or preferred cement. They'll have their own SCMs that they prefer to use or can access. They may have certain mix designs or strength classes that they're looking for, different water to cement ratios, and of course their own admixture supplies. So we've seen this technology perform across a range of these conditions you can find in industry. And just as an example, we just have an example of 7 mixes, just ordered by strength class, really. Different water to cement ratios. They have different cement contents. They have different SCM contents. This data will be published in the paper in the near future. I just grabbed the figure to drop it in. And the question often comes up in admixtures today, what about limestone cements? So we've seen a bit of friction. If you're a frequent user of LinkedIn, it's not too hard to find someone grinding their teeth about limestone cements and what it means for them making concrete. And we've had a bit of a challenge too. Up until limestone cements came around, we're like, okay, you tell the producer you want to use this technology. We believe there'll be a dose somewhere between 0.05% and 0.3% that you'll find the optimum performance. And we start doing that with limestone cements, and on the left, we don't see anything. So what's going on? Well, just like lots of admixtures, it turns out maybe you just have to bump up the dose of the admixture. So in this case, we doubled the dose from 0.2 to 0.4%, and then we start unlocking a 7% strength benefit. In this case was a customer from Europe, a 30 MPa mix design, and they had, it's not a limestone percent cement per se, but there's 14% limestone filler in this binder system. All that said, how are strength gains arising? So we've done a little bit of fundamental work. This is just some paste activated with CO2. We arrested the hydration at 5 minutes, and we put it into a microscope, and then we did some backscattered electron micrography, and we could identify the elemental distribution of what we're looking at. And so just we have a little key on the side. The silicates are in green, the illuminates yellow. What we do see is in the CO2 case, we get evidence of in-situ formed calcium carbonate. And then the other thing we can do with the data, now that we know where the different elemental compositions are, we can start looking at the phases themselves. And if we examine the low density CSH, the calcium silica ratio, we can see in the sample that's 5 minutes old, we have a much lower calcium to silica ratio in the CO2 activated system version of that product. And if we look at the later forming high density gel, again, we're seeing a much reduced calcium to silica ratio at that observation. Later, the differences aren't so much, but if we look at the science of calcium silicate hydrate, we look in the literature, we see lots of evidence that a lower calcium to silica gel is a stronger gel. And we have done, when this is now submitted for publication, when it does get published, this is paired with some nano indentation work to show that the nano indentation of the gel in the CO2 system is stronger. So we believe that's not the entire answer. Why does that explain why there's a strength benefit at 91 days? But it's a piece of the answer. So if you have this extra strength to play with as a concrete producer, great. Maybe your customers will be like, thanks for the extra strong concrete. But in practical terms, it gives you an opportunity to use your materials more efficiently. So in this case, the producer, just making a 3-way comparison, dark gray is the reference. They took out 5.5% of the binder in the light gray. We saw the strength go down. But if you brought the CO2 in on that batch with the 5.5% reduced cement, you could enhance the strength efficiency of the cement that is there and recover sort of the loss you had in performance. And so we see, again, if we're just looking at the cement intensity, in this case, it's metric, so lower is better. So we have increased or decreased, improved the cement efficiency. In longer performing data, of course, having strength benefits that might be 5, 6, 7, 8%. You won't always see them if you're just comparing 3 breaks against 3 breaks. So we can look at longer performing uses of the technology where they've been using it for a period of time, comparing higher or bigger data sets. So we have 30 samples in the orange curve, 19 in the black curve, and we have a 5.5% cement reduction in the orange curve. And with the CO2 added, we're not seeing any loss in the performance of this concrete. If you take that cement reduction and you see what does that mean environmentally, obviously the cement is the most carbon intensive component of the concrete mix. So if you're using less of the cement, you can start talking about a CO2 savings. So if you just total that up for this mixed design, it's about 138 kilograms per load of concrete of CO2 saved. In terms of durability, you go back to 2014 and we're starting to do this, and people are like, oh, you're carbonating the concrete, and now my concrete has a durability issue. And so it's something we tried to test out of the gate before we even started doing anything with more permanent installations. And we find, well, first of all, it's not carbonation. This is using CO2 as a chemical to activate the hydration of the cement. It's a small amount of CO2 compared to what you're talking about when you say atmospheric carbonation that reduces the pH of the pore solution. And it's happening when the cement paste is fresh, so that cement paste can bounce back. If you put the CO2 in and it does anything, the cement paste is still hydrating, and so the CO2 itself is not doing anything to the durability. So we have some recently published work in the ACI Materials Journal that dealt with some durability testing that was done in Chicago as examples of some of the data there with Coulomb testing on that side, and then we have the length change measurements, and so there's more in this paper. But the big question, if we go back to, oh, you're carbonating the concrete, and now my pH is going to go down. The answer is no, you're not, but yes, you are. It kind of really depends on what you're looking at. If you look at in-service, no, you're not making any difference to the pH in service. If you look at the first 5-10 minutes of hydration, yes, you add CO2, you do drop the pH of the solution, but you're only dropping it 0.5 point or something like this. So it's not acidifying the solution in a way that's going to really change the chemistry of the hydration process all that much. Now, this technology is intended to reduce the CO2 footprint of the concrete. It's not meant to be a sustainability answer and say, only do this and you've solved the problem. It's meant to be a tool you can use to help reduce the CO2 footprint of your concrete. And if you're going to look at this, you have to figure out what are the environmental impacts of following this technology. So obviously the CO2, just like a chemical, there'll be emissions associated with processing, capturing and compressing the CO2, transporting the CO2. Then we have the equipment itself, whether it's a cryogenic tank or injection system, that has to be created for this purpose. So there's raw materials involved. They have to be transported. They have to be operated. So we have all these different effects factoring it. So if we look at what estimated impacts would be just for a generic United States energy grid emission of 336 grams of CO2 per kilowatt hour, those will impact how much of an impact the CO2 capture is. Those will impact how much of an impact comes from the hardware operation. So if we're going to a dirty grid, this number and this number increase. And then otherwise, the rest of it is just kind of normalized over the lifetime of the operations of the technology. So you can see the biggest things that we're concerned about would be capturing the CO2, transporting the captured CO2, the cryogenic tank itself, and then operating the injections. So if you take the summary of this, it's about a 12% emission associated with doing a dose of CO2. About 12% of it is an emission. And if you talk about the vented, the non-mineralized portion, which is about 10% of the dose, then you get to about 22%. So in practical terms, if you dosed us down in the corner, if you did 1 kilogram of CO2 dosed, you would emit around 200 grams of CO2. You would mineralize around 900, and you would have a net removal of over 700, or 70, more than 70% of it. If we compare that to other chemical admixtures, we can see that the CO2 footprint of CO2 as an admixture is pretty low compared to the alternatives. And I think we saw that in the previous presentation just quickly. If you take these other admixtures and you look at doing them at different dosages, the more admix you put in, the greater the CO2 footprint of the admixture in your unit of concrete. And CO2 is down here. And in reality, if we're just taking this data from the European Federation of Concrete Admixtures, their EPDs, for this purpose, I only used what they call their A1 to A3 portion of their LCA. That is to the gate of the facility producing the chemical. And in the previous slide, when I'm talking about CO2, I talked about delivering the CO2 into the concrete. So it's a bit more of an LCA consideration than what I'm drawing from the EFCA numbers. So that means if I went back to the EFCA numbers, they're probably even a little bit higher. And if we went back to the CO2 numbers and say, well, we're just excluding the mineralization in this consideration, then it would be a bit lower. So the CO2 would actually be negative. If you combine what this technology is doing, a mineralization of CO2, creating more efficient hydration cement, giving you a capacity to reduce some cement, you can combine these things into a carbon benefit. And through this methodology by Vera, and it doesn't say it anywhere, Vera, they're one of the people who make these carbon reduction methodologies meant to incentivize the adoption of new technologies. What this would allow us or anyone else, and there are others, who are mineralizing CO2 into concrete to do is to look at their process and through an LCA, confirm that it is leading to a CO2 reduction. Provided they have the necessary data, they can issue what are called verified carbon units. So it's like our technology helped to reduce the environmental impact of society by 1 ton. And those tons of CO2 can be sold on the voluntary carbon market. So you have companies like Microsoft and Stripe. They're looking to say, we want to be carbon neutral, going back to, in Microsoft's case, 1977. So what can we do? We'll buy tons of CO2 reductions today and apply them against our historical balance. So there's a market for this kind of activity. In closing, this technology has been shipping out concrete for about 5 years. Until recently, where there was a bigger project in Indianapolis, a hospital. This was the biggest project our technology had been used on. This is Amazon's HQ2 in Arlington, Virginia. There's about 700 contracted users for this technology around the world in 30 countries. We've done over 30 million cubic yards of concrete, and the technology has saved 250,000 metric tons. And so the way this has possibly resonated in the industry amongst these users is because it's allowing them to be more sustainable. It's allowing them to save some costs if you're reducing your cement. It's allowing them to speak a little bit differently to architects, saying we've done something a little bit different in concrete sustainability. You can still do your fly ash, your slag, and all that stuff, but this is something a little bit new that changes, it opens people's eyes. If you wanted to do any further reading on some of the things that were thrown in there, we've tried to publish this stuff in journals, our work, so you can pick it up there. Thank you.
Or two? Go ahead.
You can answer them here.
No.
Oh, that's mine.
So, yeah. So what levers, in other words, if you're looking at the materials, and I think, one of the examples you gave was 1L cements.
Yep.
And the dosage went up. So do we know, is it the limestone? What levers are impacting the efficiency and the dosage rate required? And if you have things like Blaine or other things that are impacting that, how do you anticipate what that dosage change should be over time in your concrete? Or are there other physical properties to mixes that can change that impact that? So you have to be very specific on your application with a specific mix.
Well, part one is that since developing this technology and getting it industrialized, we've developed a lab version of the technology that wasn't there from the start, which allows us to take a customer's materials, figure out, here's your mix design, here's the dose you should use, at least based on lab guidance. So that's a way of pre-screening an effort that might otherwise have to be done in the field. The second, or the first question, why? Why would there be higher dosage? Would love to talk to people in the admixture industry who are seeing the same things. I have a few thoughts, but they're probably a bit premature.
But levers just in general as far as variations and the things that happen over time in cements, or if you change from one cement to another. Positives, blames, changes,
Yep.
what impact, do we know what those levers are?
Really, I'm in the research lab. I need our users of our technology to give me feedback on what they're seeing. So I'm a bit limited in how I can comment on that question, but the answer is probably out there somewhere.